Okay, and we're on. So this is weird. We're the only ones here. Where is everybody? As you you pretty much definitely know by now that City College has suspended all classes in the wake of the coronavirus, and so we want to contain the spread or whatever. So basically, we're moving all the classes online, and in the coming weeks, I'll update you guys on what that will exactly look like. But in the meantime, I'm going to continue to record lectures. I'm going to provide a way for you to ask me questions, and we probably will move to something more interactive in the coming weeks. Until then, we're actually just going to keep grinding, as they say. We are going to continue moving on with the lessons. I'm just going to be here talking to myself for the whole time. But hopefully you guys can get what's going on. And if not, ask me questions and we'll address them as time will go on. Kind of weird. I've actually filmed a few classes like this already, but I'm still getting used to having no one to talk to but actually the camera. Sometimes I'm not even sure if I'm looking directly at the lens. So if I'm looking off somewhere and it just bear with me. So let's actually just jump into it. Last class, we finished up by talking about the ratio test. So just to remind you of not the ratio test, the root test, right? So the ratio test we did just before this. The last test we spoke about was the root test. This was test number 9 or whatever. And basically the test works on any series pretty much. So given any series, we can actually compute this limit, and remember the limit is always as n approaches infinity, of the nth root of the absolute value of the sequence formula. When we're computing this limit, we can make 3 conclusions based on the result of this limit. So if the limit, which clearly has to be a positive number, if it's less than 1, then the series converges. Not only does it converge, but it converges absolutely. Now, remember what that means. That means that if I were to put each term in this series in absolute values, that would still converge. And I also spoke about why that was important. That pretty much ensures that we have commutativity of addition in the infinite summation case, and that's pretty important, as we'll see moving forward. So if this limit is less than 1, the series will converge absolutely. If it's bigger than 1, the series will diverge, and if L is equal to 1, you can make a conclusion from this test. Another thing that I mentioned was the conclusions of the root test are very similar to that of the ratio test, meaning in cases where this guy's inconclusive, the ratio test will also be inconclusive. So you're probably never going to be in a situation where you'll actually try to apply both of these tests at the same time. So if your root test is inconclusive, the ratio test wouldn't be something that you try, and vice versa. Other than that, we left off with an example. I left you off with several examples, but this was the example that corresponding to the root test, and then there were about 4 more general examples that I wanted you guys to try, but I'll actually talk about something before going over those examples. But in the meantime, let's just actually see the root test being applied to something. Okay, so this is the root test. Here's some random series. Now, of course, you know that we're going to use the root test here, but in general, you won't know that ahead of time, I'm going to talk about how to know which test to pick in general. But given this, notice that one thing that would kind of scream out to me that I would want to use the root test is this nth power right here. You see, the root test requires us taking an nth root, which means it is particularly useful to simplify things that have the power of n. And so this here is my an here. And so what I'm going to do is I'm going to set up this limit. Set L equals to the limit of the nth root of the absolute value. of that guy. Now what's going to happen? The nth root, of course, cancels that. And so now I just have the limit of 2n plus 7 over 7n minus 3. And that limit is, that's right, 2 over 7. It's going to be like Blue's Clues. What is the answer, kids? 2 over 7, that's right. Okay. But word of caution here, this is going to apply for as long as we're doing this sort of thing. Whenever I make a pause in the video, or I ask you to, hey, pause the video and try this problem, then it's very important that you pause the video and try the problem. Because just watching me do all the examples is not going to be as useful to you as you might think. We all know those students who show up to class every day, on time, they pay attention, and they still do bad on exams. Because watching people do math isn't the same as getting good at math yourself. So if I ask you a question, try to answer it. And if you get it wrong, no one's going to know because no one's around. But you're going to know, and then you're going to try to correct yourself. It'll also give you, tell you what kind of questions you might want to ask me whenever we get to interact. And so really actually try the problems before I actually go through them. Give it a shot. You'll see where you are getting stuck or what is confusing you or something you don't understand. You should ask them in terms of, for now, what we're going to be doing is, if you have questions, you can put them down in the comment section or something like that. If you want it a little bit more anonymous, you could actually just send me questions through Jupyter Grades just to keep things all in one place. I'd rather you send them to Jupyter Grades because my other emails has, you know, we're in a state of emergency. I'm getting a lot of emails from a lot of different sources and I want to make sure I'm not missing any questions. So if you have any questions, you can drop them right down in the comment section or just email me through Jupyter Grades and my students know how to access that. So the limit of that is 2 over 7, and what's so special about 2 over 7? Well, it is less than 1. What happens when the limit is less than 1? Well, the series converges, and not only does it converges absolutely. So that is an example here. So I can take some time to copy that down or make sure you understand what happened. But it's basically just me applying this test, the root test, which, yeah, in and of itself, not that bad. None of the tests individually are bad. As I mentioned, the thing that you have to look out for is that on a test or a quiz, whenever I'd be able to give you guys one of those things. I'm not going to tell you which test to use. You're going to have several different series. They're going to have be of several different varieties. Several different tests might work on them or not work on them, and you kind of have to know basically how to choose. But that is the root test, and that's an example of me using the root test. Now, to just pick up on what I just mentioned, I think before going over the next few examples that I left for you guys, I actually want to talk about when to use which test. What are you going to actually try when you have to actually talk about whether or not a series converges? So, just like with integration, I'm going to give you like a strategy for how you want to approach a random series if your goal is to talk about whether it converges or diverges, or whether it might converge absolutely or not. And just before the strategy, that's something else I want to talk about. So there's something that some textbooks refer to as the absolute convergence test, which in and of itself is not really a test. But we'll call this the last test, even though technically it's not a test. So maybe this is 10? I don't remember. Okay, so telescoping series was 0. Test for divergence, 1. P-series integral comparison, limit comparison, ratio, root test, alternating series test. maybe this is like 9. So it's really like 10, but we start from 0. So this is 9. The absolute convergence test. And basically this is just to test a series for absolute convergence. You must test this series, right? And technically, why I say this is not really a test on its own, because it doesn't really have rules that are associated with this test. You're going to test the series when you put absolute values on each of the terms using one of the other tests that I already told you about, using some other convergence test. The only exception is it's not going to be the alternating series test. Right? So the alternating series test is never going to be applicable when you actually want to test for absolute convergence. So that's something that you should know. But other than that, you put absolute values around the guy. And if this guy converges, we conclude that the original series converges absolutely. It's also worth mentioning, if this series diverges, n itself, the original series, may still converge. This is called conditional convergence. I mentioned this to you before, but let me just remind you. This is called conditional convergence. Use another test to determine this, and this time the alternating series test would be included. It's called the absolute convergence test, but in and of itself, it's not really a test per se, because to actually determine whether something converges absolutely, you're actually going to use one of the other tests that I actually already told you about. So I'm going to chalk it there. But yeah, testing whether something converges absolutely is going to be very important, as I mentioned. Absolute convergence is a super important thing. Now, so you can take a little while to copy that, maybe pause the video, give you 3, 2, 1. Okay, so pause the video and copy that in that 3-second window if you need to. What I want to do now is to mention a certain very common problem type and how you want to approach that problem type. So, common problem type. The word is going to be very similar to this. It's going to say something like, determine whether the following series converge absolutely, converge conditionally, or diverge. And you'd have usually a bunch of examples below this, 2 or 3, 4. So they'll have A, B, C, D, right? And on your first test or whatever, we're still have to figure out testing, because the math department thinks, and I totally agree, online testing isn't really, we know what goes on in online testing. So we're still trying to figure out how we're actually going to give tests. Hopefully within a week I'll have some answers for you and I can tell you about that. But on a test, traditionally speaking, you would see a problem like this, pretty much exactly like this. You'll have three to four parts. So on test number 1, I would have given you a question like this for sure. It's a very common thing, and there's a certain way that you're supposed to approach it. So this is a common problem type. Okay? Now, that problem type you should appreciate. It's very different from if I were to ask you, does the series converge? Right? Me asking, does it converge absolutely versus conditionally versus diverge, that is a little bit more specific, because converge actually includes both of these. Right? Whether something converges absolutely or conditionally, technically it converges in some sense. It's just that the absolute sense is a lot more concrete, a lot more useful, and a lot more better, and it maintains a lot of our other mathematical rules that we'd like to maintain. Absolute convergence actually maintains them better, but you might want to determine whether a series will converge conditionally also. Now, how you want to approach these? You are of course going to use one of the 10 or 9 series tests that I already told you before, but you definitely want to go in a certain order when approaching these problems. So, how to do this problem type? And by the way, this was the phrasing, if I recall correctly, that I used to give you the last 4 examples from last class. I think I wrote it out this way. If not, then I meant to. So just redo all the problems with these instructions. Now, as far as approach would go, how would you actually want to approach these? Is 1, you want to check absolute convergence first. Okay? And so you have a couple possibilities here. So if I ask you this problem type, I give you a bunch of series. What you're going to do is you're going to first put absolute values around each terms of all those series, and then you're going to run a test, right? This is called checking for absolute convergence, right? Now, there are a couple things that could happen here, obviously. If the series converges, you would conclude AN converges absolutely. Okay? Now, if this diverges, move to step 2. Now, in step 2, what you're going to do is you're going to check for conditional convergence. Now, basically what that means is that you're now going to remove all the absolute values and just test the original series as it was originally presented. So, if I ask you this kind of problem, the first thing you're going to do is you're going to put absolute values around each term of the series. You're going to do one of the series tests I taught you to determine whether it converges or diverges. If it converges, you stop, you conclude, hey, the series converges absolutely. If by doing that you get something divergent, you're not allowed to conclude outright that the series diverges. You have to check whether it converges conditionally. So what you're going to do then is you're going to remove the absolute values that you put in and just test the original series using one of the other series tests, including the alternating series test. Once you're in step 1, alternating series test is off the table. It's never going to be used to determine absolute convergence. Alternating series test always tells you about conditional. Here though, any test is fair game, and so you would actually do that. It's also worth mentioning that the ratio and root test give you absolute convergence as the conclusion. So chances are, if you figured out that it's not absolutely convergent, the ratio or the root test will be inconclusive, or it would tell you straight out that it diverged in the first place. So you'd be able to make conclusions based on that. But in general, you put absolute values, you test it. If it converges, you say yes, it converges absolutely. If it doesn't, depending on the test, for every test except the ratio and the root test, you would have to check conditional convergence separately. So here is, so check for the conditional convergence. Now, you again have two options here. If this converges, you would conclude the series AN converges conditionally. If this diverges, here's where you can say for sure that everything is going to diverge. Conclude AN diverges. Okay. Now, as I mentioned, each test has this little nuance. For example, the test for divergence. Once you use the test for divergence to conclude that something diverges, then it diverges. None of this is even going to matter. Test for divergence is one of the things you're going to test first. I'll talk about that in the approaches soon. But in general, for the typical problem, it's kind of a two-step process. The process starts with absolute convergence, right? It has to start with absolute convergence. The reason being is that sometimes you can check something for conditional convergence and it works, but you're not going to know that it converges absolutely. So you'd have to go back up and check that. So you'd end up having to do twice the work instead of just doing one test. Whereas if you check for absolute convergence and it works, you don't need to check for a conditional convergence. So it can potentially save you some time. So if this is the problem type, then this is what you want to do. You want to check absolute convergence first, check conditional convergence second. Okay? So that is just an approach for this particular problem type. Now, let's talk about an approach in general, right? So for a random series, right? I give you this random series. Does it converge, whether absolutely or otherwise? How do you know which of the 10 tests that you're going to try to use, right? Because for integration, we had a bunch of different methods, and we actually even had less methods than we have now. I think I showed you 8 techniques of integration, right? You know 10 techniques of series, right? So there are more things to actually know here. They're not as difficult as integration, I don't think, but it's still a lot of things to be thinking about all at once. So roughly what order do you want to be thinking? If I give you a random series, how do you want to check, how do you know which test to apply first, right? What do you do first? What do you do second? What do you do third? What should you be thinking about? Where should your mind be going for certain series? That's what I'm going to talk about right now. So like a general approach to determining series convergence. So I'll talk about that, and then we'll actually go through the 4 problems that I left you guys with. Hopefully you guys tried those 4 problems. Whether or not you did it the most efficient way, I don't really care at this point. You actually having tried them is more important to me. However, if you haven't tried them, what I would like you to do is to pause the video before I actually do them for you and try them on the spot, then start the video again and see if what you did kind of coincides with what I did. That's probably how you're going to want to approach this. Okay, so let's talk about that. General approach. So I give you some random series. I'm not even tell you what the formula even looks like because I don't want that to matter too much. How do you know whether something converges or not? So, step 0. So this is really something that you should be trying to figure out right off the bat, step 0. Try to test for divergence. Right? Now remember, the test for divergence only tells you about divergence. It does not tell you about convergence. And what that is, you might recall, is you're going to take the limit of an as n approaches infinity. If the limit is not 0, it diverges, meaning you don't have to check absolute convergence, you don't have to check conditional convergence, it will not have any kind of convergence. So if the test for divergence tells you that your series diverges, that's it, it diverges. Like there's no way to actually save it. The only way a series can converge is if the limit approaches 0, but even in that case it might not converge. So if the limit is 0, you don't know, you have to do some other test. But if the limit is not 0, then it will definitely diverge. And because you've been doing limits since Calc 1, you have a lot of experience with limits, it's super easy for you to find a limit right now. That's the first thing you're going to look for. So that's it, step 0, test for divergence. Just look at the thing. Is the limit 0? No. If it's not 0, diverges. Nothing else to talk about. Step 1. Now this is a step that helps us deal with the reality of how things are being tested. So depending on the question type, you might want to do something else. So if asked what a series converges to, so remember, our tests, most of them, just tells you whether or not something converges. It does not tell you in general what it would converge to. What is the thing that the series converges to? Except for 2 of our tests. It's either going to be telescoping, if I ask you this question, or it's going to be geometric. Look at the form. So geometric has a very specific form. I told you what that is. So you should notice if something is geometric or not. Now, if you notice that it is not geometric, and I ask you what specifically does the series converge to, then you know it's telescoping. It's going to be like do partial fractions or something like that to kind of break things up and cancel it, right? So sometimes just depending on how I ask the question can actually tell you a lot. If I ask you, determine whether or not this converges, it's very different from me asking, what does this converge to, right? There are only 2 tests that tells us what the answer would be if they converge. That's the telescoping and the geometric series test. So if the question is phrased that way, it's going to be one of those 2. So just figure out which one. The geometric looks like am I even pointing at the right thing? Right. So the geometric series test has a very specific form. So you should be able to recognize that right away. If it's not that, then it's going to be telescoping. So you'll know that way. As well as if asked, do the absolute convergence test. I really have a problem calling it a test. Maybe a method would be better. Method. Right, meaning you're going to first put absolute values around it, do some test, then take it off if necessary, do another test, so on and so forth. Right? So, step 0, test for divergence. Once a test for divergence tells you something diverges, it diverges. That's the end of the story. If I ask you specifically, what does this converge to? Boom, that is going to be either a geometric or a telescoping. You should be able to recognize the geometric pretty easily. If it's not geometric, you know it's telescoping. Just do partial fractions or something like that. If I ask you, does this converge absolutely, or conditionally, or diverges? Then you're going to go through the absolute convergence method, which I wrote down on the board just before this. So yeah, that's pretty much step 0 and step 1. Step 0 always tries before. Step 1 is you might vary your technique based on how a question is phrased, or notice something based on how a question is phrased. Now, assuming that the question doesn't give you any other clues, what is the next thing you're going to look for? Well, step 3. is to use use tests that require a specific form if the forms present themselves. Okay, what does that mean? There are 3 series tests in which the form of the series itself is very specific to the test. One was the geometric. So that looks like AR to the n if you start from 0. And it looks like AR to the n minus 1 if you start from 1. Right? So that has a very specific form. So you should be able to spot that form anytime it actually shows up. 2 is the P series. These guys also have a very specific form. 1 over n to the P from 1 to infinity. Right? So you should be able to tell whether that converges pretty easily. The other one is the alternating series. So pretty much you see something like a minus 1 to the n an. Right? So I give you a random series, and I would say these two, in these two here, order matters. And from now on, no particular order. Right? So this is not necessarily the third thing you think about exactly, but it is something that you should think about, provided you actually see one of these 3 forms. So if it's geometric, you should notice it's geometric and actually try the geometric series test. If it's a P series, you should notice it's a P series. Try the P series test. If it's alternating, you should notice it's alternating and try the alternating series test. There is an exception to this. And remember, the alternating series test only conditional convergence. Right? The alternating series test cannot tell you about absolute convergence. So if a problem asks you specifically about absolute convergence, then using this test right away is not a smart move. It's not a good idea, because that test cannot tell you about absolute convergence. So yeah, so one of the first things you're going to want to look for is things that have a specific nature, a specific form. You're going to want to know, you're going to want to notice those guys, know the test, and just apply the test. So that's the third thing. The third thing. It's not necessarily in a certain order. Here's another thing that might depend on form, though it's not as super specific as these. I don't know, maybe I should have left the title up. I don't know. Too late now, we don't look back. Okay, so if an is rational, or close to it, use a comparison test. So rational, you know what rational looks like, a ratio of polynomials. What do I mean by close to rational? I mean something where it would, so what does like close to rational mean? Let me give you an example. So something like n squared plus 2n plus 7 over n cubed minus 7n plus 1. So that would be a rational, but if this had like a radical over it, it's still kind of close to being rational, right? And the idea is you kind of want to just ignore all the smaller guys, and you can actually write this as a power function. So when I say almost rational, or close to rational. If you want to go by some definition that I have in my head, what I mean is if you ignore all the little guys, what you have left over is a power function of some sort. So comparison tests are very convenient in that situation. Now remember, there are two comparison tests. There's a direct comparison test. That one requires you knowing who's bigger or smaller. There's also the limit comparison test. If you don't know who's bigger or smaller, use the limit comparison test. That's basically the idea. I'm not going to go over the tests. I already told you what those tests are about, but comparison test is very convenient in the rational function case. Like I said, it's not necessarily step 4, it's just if you notice a pattern, might not be in an order. Step 5, what is something else that you want to look for? If an includes factorials or exponentials, or specifically exponentials with really weird exponential powers, try the ratio test. Okay, now remember the ratio test also has certain restrictions. You can't use the ratio test if any of your terms of your series hit 0. However, other than that requirement, there really is no requirement. I showed you last time why it's actually convenient in terms of factorials, because once you start taking the ratio of factorials, it allows you to cancel a lot of stuff. So if n includes factorials or exponentials, you'd probably want to think about the ratio test. Moving on to step 6. Very close to the ratio test is the root test. If your terms look like some other sequence raised to an nth power, try the root test. Right? So if you just have something raised to an nth power, or a constant times an nth power, the root test might be very convenient because you take the nth root, so you'll actually get rid of that power. So you notice factorials, or it looks really complicated. The ratio test is a good guide to use because it allows you to cancel stuff and reformulate into something else where you can talk about a limit easily. If you notice something is just like boom to the nth power, the root test is pretty good. Again, step 5 and 6 would pretty much never be used in conjunction, because where one fails to give you a conclusion, the other one is going to fail. So remember that, keep that in mind. So the ratio and the root test, they make very similar conclusions. If one converges by the ratio test, the root test is going to show convergence. If one diverges by the ratio test, the root test will show divergence. And if the ratio test is inconclusive, the root test is also going to be inconclusive. So don't waste your time actually trying to apply both of these at the same time. Let's make a note of that. Do not apply it together. Okay, what else is there? Step 5, step 7. Suppose if an equals fn. So we're gonna, essentially what I'm saying here is think of an as a real valued function. Meaning it doesn't only take integer values, real valued function. And you notice that fn, or f of x, is easy to integrate. Okay. Now by easy to integrate, of course, the assumption is you're really good at integration at this point. So you'll be able to look at that and say, hey, you know what, a substitution, I could use that, solve that by substitution. Or, hey, you know what, if this was a function, I could easily use an integration by parts here. You can, if it's easy to integrate, try the integral test. Provided the conditions are met. So remember, for the integral test, you needed to only have non-negative outputs, you need it to be continuous, and you need to be decreasing. So once you have something that's always outputting 0 or bigger values, it's decreasing and it's continuous, and you notice that it's easy to integrate, the integral test is actually going to be a pretty good bet as to tell you whether about convergence or divergence of the series based on how its corresponding improper integral behaves. So I already told you about the integral test, so look that up if you don't remember. Let's see, what else is there? I think that's it. I think that covers all the bases. I don't think there's any scenario that I would ask you about in this class that wouldn't fit under one of those 7 steps. Let me check my notes here. Yeah, that's that basically covers everything. So you should have those in mind when approaching any series. And speaking of which, I gave you several examples from last time. So let's actually go through those. Let's actually try to apply our strategy to the examples from last time. So the question was, converges absolutely, conditionally, or diverges, right? And we had several examples. N goes from 1 to infinity, cosine squared n plus 1 over n squared plus 1. B, series n goes from 1 to infinity, of minus 1 to the n, cosine of n factorial over n to the n. Third example, n goes from 1 to infinity, minus 1 to the n, n over n plus 1 to the n. And the last example, so imagine this problem showed up on a test, right? Or a quiz, whenever I'd be able to give you one of those, right? So I said, oh, determine whether the following series converge absolutely, or converge conditionally, or diverges, right? And then boom, 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 A, B, C, D. I give you these 4. What do you do? Okay, so we're going to take these one at a time. And again, remember, before I do it, pause the video and actually try to do the problem yourself. You're essentially shooting yourself in the foot if all you do is just watch me do everything. Really, it's important. You'd be surprised to know how the difference between like getting an A in a class and just outright failing it or really struggling with it, being frustrated, can be some very simple habits. Simple habits like being engaged in class, asking questions in class, or actually trying problems before seeing me write down the solutions. You have no idea how much those 2 habits alone can really drastically change your trajectory. It's not even funny. It's night and day. You know, there are a lot of times where you might think, oh, that the smart kid in class who's always getting all the questions correct and he always gets good grades on tests and stuff like that, you might think, oh, he's smart, you know, he was just made for this or something like that. But usually the answer is a lot simpler, and it's something that could be replicated by many people. Now, I'm not saying there aren't geniuses out there, but I'm saying there are a lot fewer out there than people tend to think. Like, most people never have met a real genius. But the people who do better, they're outworking you most of the time. That's the only story. And we don't really see this happening, right? Because a lot of the work happens behind closed doors. So a lot of times students might see that one kid who is answering all the questions in class and getting them all correct, and they're like, oh, he's just a math person. But they don't realize that behind the scenes, that's the kid who sends me emails. That's the kid who, when I give homework problems, he does the even as well as the odd problems. And that's the kid who actually shows up to my office hours and asks me questions, and they bother me all the time, not in a bad way, but in a good way. They're actually putting in a lot of legwork outside of the classroom that most people never realize goes on, right? The more you do on your own, the better it is for you. And even if you're at a point right now where you feel like you're lost, you don't get it, still trying and getting stuck is better than just watching me do everything. Because you knowing what gets you stuck or what confuses you will allow you to get better help. When you go to me or you go to a tutor, you'd be able to tell them specifically, oh, here's where my problem is, as opposed to what often happens when I ask, oh, so what issues are you having? They're like, I don't get anything, right? That doesn't help anybody. That's not helpful at all. Not to you, not to the person trying to help you. So trying something on your own, very, very important. Even if you get stuck, even if you get it wrong, you have valuable data from which you can make a plan, you can know what you need to attack, you can know what you need to get better at. So don't just wait for me to do these problems. Pause the video whenever I give you the cue to pause the video and actually try the problem, right? So these are the problems. Now hopefully you've copied them already. Give you a 3-second window to pause the video and try it. 3, 2, 1. Okay, so hopefully you copy them all down. So we're going to take them one at a time, but I would like you to try them before I actually try them, right? And it's okay if you don't know. Write down the steps that I just gave you, have them written down, have them beside you, and actually try to look at the problem and look at the steps that I gave you and see which one of these kind of matches with what Jhevon is talking about. As well as, because of how the question is phrased, I told you how you're going to want to approach these problems, so that should tell you also right off the bat. Okay, so let's attack the first one, problem A. The series from 1 to infinity of cosine squared n plus 1 all over n squared plus 1. So, pause the video right now. Pause it. Press the pause. I'm waiting. Okay, good. Try it. Okay, are you back? Did you attempt it? Did you? If you didn't attempt it, pause the video and attempt it. Okay, so I'm gonna go in and do this now. Okay? Now, wherever you got stuck, you should pay attention to that, because that will help you ask questions in the comment section. Oh, Jhevon, I tried this and I got stuck here. That's useful information, right? So now I know the next class I need to touch on that, or the next time I need to clarify certain things or explain something differently or whatever, right? Tell me about your attempt. It's also good for you to, several times ago, there will be many ways to skin a cat, so you might even get to an answer like I got to, but you got there a totally different way. And you might want to ask, oh, Jhevon, I did it this way, is this okay? And I might say, yeah, it's okay, or I might say, yeah, it's okay, but it's terribly inefficient because doing it my way would have been better. Or I might even say, hey, you know what? I actually like your way better than how I did it, right? Every now and then that actually happens every now and then, where a student did something, I'm like, I actually rather like that way, even more than my way. And you know, sometimes I actually mention an alternative way to do it in class. So regardless, always try a problem on your own, even if you know what you're doing, because there are lessons to be gained by finding a different route to the prize than how Jhevon did it, right? And you might find out why I decide to do it certain ways. Like I said, over the years I picked up a lot of experience, and I find sometimes I'll do something because it's the best way, it's the most efficient way. Sometimes I'll do something because I just realize that doing something else puts most students in trouble because of algebra skills or whatever. So there are times when I would actually opt to teach a less efficient method. And however, if you could pull off the more efficient method, then you should know about it and try it, and you can ask me about it. Okay, that was very long-winded. How much time do we have? Okay, so we're about 50 minutes in. That's, I don't know if we're making good time or not. But yeah, so we have like we're at the halfway mark. So we're gonna go through these slowly because I'll be explaining what I'm doing while doing this. But if you wanted a goal for time-wise, a problem like this with 4 parts, you should be taking somewhere between, I want to say aim for 15 minutes. If it gets pushed into the 20-minute time range, it's okay. It kind of just means you need to make up that time somewhere else on a test. But a problem like this, all said, should take you like 15 minutes. Of course, it's probably going to take me 2 times that amount because I'll be explaining what you'll do. So it'll probably take us 30, 40 minutes to get through all of these, but yeah. Okay, hopefully you tried it. Let's actually do it. So first of all, one thing I want you to note is that cosine squared n plus 1 over n squared plus 1 actually approaches 0. So the test for divergence is actually useless here. It doesn't actually give us any information. To prove that, strictly speaking, you'd use something like the squeeze theorem, but it kind of just makes sense. Cosine is going to be the largest possible value is 1, which means the numerator, the largest the numerator could possibly be, is going to be 2, and the denominator is a quadratic, right? So the denominator is going off to infinity, while the numerator stays very small. It's going to go to 0. So we know that it doesn't necessarily diverge, right? We don't know if it converges yet, but we don't know enough from the test for divergence to talk about that. Now, because the problem asked me about absolute convergence versus conditional versus divergence, the first thing I check is absolute convergence. Which means I'm going to look at this series and I'm going to put absolute values around it. Now my goal is, for the next few moments, try to figure out if that guy converges, right? Now, it's a trig function, and I put absolute values around it. By the way, if you check, let's say you messed up already so far, now that I told you that that would be the first step, pause the video, actually try to finish this step here. Okay, pause it, try it. Okay, I'm going to assume you tried it. So if you didn't get up to this point, start from this point. What I would do is the following. It is a trig function that is now bounded by absolute values. I know how cosine deals with absolute values. Cosine and absolute value is less than or equal to 1. Cosine squared is also going to be less than or equal to 1, which means that this series here is actually less than or equal to 2 over n squared plus 1. This is a guy that fits the bill of being almost a rational function, meaning once I put him in absolute values, I can actually use some sort of comparison here. Now, I could go better. I could make the denominator smaller to get a bigger fraction and use that guy. And to make it look even nicer, I can factor this 2, put it out in front, because now this guy here has a very special form. I know what that does. This is a convergent p-series. It is also worth mentioning that since I put absolute values on this guy, this is greater than or equal to 0. Therefore, I have my original series, it's greater than or equal to 0, and it's less than or equal to this guy that I know converges. That tells me by the direct comparison test that this guy converges. Let's call this AN. So this here is referred to as AN. So AN converges by comparison. This implies that the original series converges absolutely. So our first example was an absolutely convergent series. Okay, so take some time to copy that. Now, if you got something different, you are going to want to make a note of that you got something different. Like, for example, if you tried this and you got that it diverges, you couldn't be more wrong. First, so don't be embarrassed about that. There's no one here to find out that you got that wrong. It's our little secret. But you should realize why you got that wrong, or if you don't even realize why you got that wrong, just ask me. Again, throw the question down in the comment section or email me at Jupiter Grades and just like, hey, Jhevon, I tried that problem and I got that it diverges. Here's what I did. Where did I go wrong? I'll address it next time. So that's an absolutely convergent series. So again, step 0, do the test for divergence. Then move in to check for absolute convergence. At this point, it actually converged, so it converges absolutely. That is the end of the problem. All right. Let us move on to the next problem. Okay, you know what to do. Pause the video and try it. Pause it. Did you pause it? Looking at you. Pause the video, try it. Okay, we're back. All right. So, hopefully you tried this. Step 0 is where we'd start, of course. What is the limit of this guy? Okay, all together now. Well, we know about that rule that I've mentioned many times before, that as n is going off to infinity, logs are smaller than polynomials, which are smaller than exponentials, which are smaller than factorials, which are smaller than the variable exponential. I wonder how that looks. I'm actually running low on white chalk, so I might switch to yellow eventually. It's because I have to special order my chalk. It's Hagoromo. But I have to order them specially. I ordered some, but it hasn't gotten here yet. So I'm really running low on white chalk. Might switch to yellow. But yeah, so this means this guy is much larger than that guy's and is going off to infinity. Notice that that guy's in the denominator of this fraction, which means the inside of that cosine is approaching 0 because it's a bottom-heavy fraction. So that limit is actually the cosine of 0, which is, altogether now, that's right, it's 1. What's so special about 1? Well, in particular, it's not 0, which means, that's right, the series diverges. I test for divergence. Hopefully you got that one. If you didn't get it, what did you do differently? Did you think it converged? I don't know. But that's that. Now again, it's worth mentioning that if we did get the limit being 0, we couldn't actually make any conclusion, right? So you would have to do something else. But here the limit is not 0. We can conclude that it diverges. So take some time to copy that down. I'll give you 3 seconds. 3, 2, 1. Let's go. Let's go for the third series. Now there are a couple ways to do this one. So the first way I'm going to do it, I will readily admit that the average Calculus 2 student is not going to see it this way. They're not. But I'm going to do it this way just to make a point. But then I'm going to do it another way, probably how the typical Calc 2 student would actually approach the problem. So step 0. We're actually going to try the test for divergence, but I'm actually going to approach that probably a little bit differently. So, check the limit of this guy. Now here is something strange, because this, I kind of notice a pattern going on here that I'm not, that you're probably not seeing. So first of all, one thing you should notice is that this is an indeterminate form. That approaches 1 to the infinity, which is indeterminate. And so most, the traditional way to deal with that would be to just like get an ln in there, move the power down, and actually try to use a L'Hopital rule kind of thing, which I will actually do that way second, but there is actually a pattern that I can take advantage of here without going through all those hoops. Let's look at the reciprocal of this guy. So I'm going to think of this as 1 over n plus 1 over n. Now, so far, some of you are probably wondering why I decided to do that. Otherwise, maybe you'd like to pause the video and try to see what I'm going for here. See if you can figure out where I'm heading here. Okay, let me actually do another step. I'm able to just divide n into each part here, so this is like 1 plus 1 over n. Now, some of you might actually start seeing what I'm seeing. No? Okay. Let's write one more step. I can actually write it like this. Notice anything? That is the definition of E in the denominator, isn't it? Once we take the limit of this guy as n approaches infinity, that is actually E. So this limit here is 1 over e. Now, that's a very special number. Why is it special? Well, it's not 0, is why it's special. The series diverges. Okay, so this is our third example is also a divergent series. Some people are thinking, Jhevon will never give us 2 divergent series in a list of problems like this, would he? You don't know what Jhevon's going to do. Jhevon's crazy. Okay. Yeah, so the series diverges by the test for divergence. So normally when you actually make a conclusion, I expect you to tell me how you made that conclusion. What test were you thinking of when you made that conclusion? So this guy diverges. Let's actually do this limit the more traditional way. So you can pause the video, copy that down, and let me do it another way. Probably the way that a typical Calc 2 student would actually do it. But that's just me doing this example to remind you, hey, you always want to have the definition of E on your mind. It pops up all over the place. Remember how it popped up in Calc 1 all over the place when we're deriving all sorts of rules. Yeah, it's a very special limit. You should see it everywhere. You should notice it's reciprocal in places. That's also a good thing. Okay, let's be like an average mortal here and do this the way that other people have done it. You could get an ln in here to bring that power down by writing it as e to the ln of that thing. And since we know limits pass through continuous functions, that was something that we learned in Calc 1. This is actually equal to e to the limit of the ln of n over n plus 1. This is equal to e to the limit of, well, n times ln n over n plus 1. Right? Because that's a log rule. We can bring powers down, put it in front of the log. Now, of course, we know the trick here, again from Calc 1, of moving someone down and taking their reciprocal instead. Now what you'll notice here is that this limit approaches, as n approaches infinity, the inside approaches 1, so the top approaches log of 1, which is 0. As n approaches infinity, 1 over n approaches 0. This gives you infinity over infinity in the power. So you can apply L'Hopital's rule. You have to say it with a French accent or it doesn't work. Right? Don't ask me why, but that's actually true. You can apply L'Hopital's rule. Take the derivative of the top and divide by the derivative of the bottom and take the limit again. One thing, just to make my life easier, I am going to think of this using a log rule. Just think of this as ln of n minus ln of n plus 1. So the derivative of the top is 1 over n minus 1 over n plus 1. The derivative of the bottom is minus 1 over n squared. Now I can multiply top and bottom by n. Or let me just do it this way. Combine the top. So this would be n plus 1 minus n. So it's just 1 over the product of the denominators. That's n squared plus n. And then keep change flip. This is multiplied by minus n squared. Now that is a rational function ratio of polynomials where the highest degree and the top and bottom are the same. So it goes to the ratio of the coefficients, which e to the minus 1. And that's not 0. And that tells you the series diverges. By test for divergence. All right, so another way to look at the problem there. Probably the more traditional way to do that limit. So you can take some time, copy that down, give you 3 seconds. 3, 2, 1. Okay. Hopefully you copy that down. Let's keep going. Let's look at our fourth example. Yep, so pause the video, try it. Give you 3 seconds to pause it. 3, 2, 1. Okay, let's go. All right, so first thing is clearly the test for divergence is useless here. Limit of 1 over ln of the square root of n plus 1 is 0, so we can't be sure that this guy diverges. We need some other test. Now, also, we know that the original question that I erased asked, does this converge absolutely, conditionally, or diverges? So, what I'm going to do here is check absolute convergence. Now, to check that, I'm pretty much going to put absolute values around this thing. How is that going to affect the guy? I'm going to essentially be looking at this guy without the minus 1 to the n on it. Okay. So now, how can I look at that guy? So, any ideas? Any ideas? Come with some ideas. Write it down or say it aloud to yourself and see what you would actually try here. What's my idea? I think a comparison is actually a good thing to do. So, look at ln of the radical of n plus 1. Well, first of all, you should notice that that is actually 2 over ln of n plus 1. Okay? Why is that? Well, we know that this guy here, well, that's just ln of n plus 1 to the 1/2, which we know we can bring that 1/2 down in front. And if that's in the denominator, then flip and multiply. I can get it. It's just 2 over 1 multiplying in the numerator. So that is actually equal to that. And secondly, having 1 over ln, not very convenient. I can't integrate that. It doesn't look like a p-series or anything like that. However, what if I were to ignore the ln? So if you haven't thought of that idea, now that I actually wrote that down, think about it. That series that I just wrote down, sequence technically, or formula, how do these two guys compare to each other? Go on, take a guess. 3, 2, 1. So it turns out we can determine who's bigger or who's smaller here. And again, we have that rule, right? Logarithms are smaller than polynomials, are smaller than exponentials, are smaller than factorials, are smaller than variable exponentials. So notice what I'm comparing is these two guys. I'm comparing a polynomial to a logarithm. The logarithm is smaller, which means the denominator of this guy is larger, and which means this guy is smaller than that guy. Right? So now, let's call this guy here an. Let's call this guy here bn. And let's look at the series of bn for a second. What can you tell me about the series of bn? Now there are tons of things that you can do here. You can just notice that bn diverges by, well, since it's a harmonic series. Right? So it's kind of like a shifted harmonic. The series of 1 over n is super similar to the series of 1 over n plus 1. You'll notice that you're still just adding up all the fractions. You're just one step ahead. Other than that, another way you can do this, or use limit comparison with 1 over n or 2 over n. Which that you know is harmonic, strictly speaking, like factoring off the 2. That's definitely, it's exactly textbook harmonic. But this one here is also harmonic, right? It's just like a step ahead in the harmonic series. Now, also what you'll notice is that for n larger than 1, this guy is definitely greater than or equal to 0. And so what that tells you is that the series of an diverges by comparison. So I can compare this series to the series of 2 over n plus 1, and I can determine that this series diverges. So I guess the answer for D is the series diverges. No, that's not the answer. You should know that's not the answer. How do we know that's not the answer? Well, I was checking for absolute convergence. Okay, so I still don't fully know everything about the original series. So one thing I do know about it, though, from this test, is that it does not converge absolutely. It may converge conditionally. So we're actually not done with this problem. So you see this, you put absolute values on it, you get that. One thing you'd want to do is probably compare the ln to just a regular polynomial. That's going to show you that this guy diverges. So it means if I put absolute values around it, it doesn't converge. Let's move on to the next thing. So the next thing that we're going to want to check, check conditional convergence. So conditional convergence just means remove the absolute values that you put there in the first place and check, does the thing converge now without the absolute values? So I'm going back to the original series pretty much. Now, at this point, you're going to think, well, what kind of series is that? What can I use? And this is pretty much from, what do I call it, step 3 in our strategy. It has a special form. It has this -1 to the n. So that tells you it's alternating. So if you want to check conditional convergence here, I think the obvious choice is the alternating series test. So if I set an equals 1 over ln of the radical n plus 1, notice that an is always positive, right? Because the log of 1 is 0, and once you're taking the log of something larger than 1, it's going to be positive because the log graph goes like that, goes up like that. Did you see that? Goes up like that. This guy is going to start, because the series is starting at n equals 1, we're starting from the log of radical 2. So that's going to be positive. So 1 over that is going to be positive. So an is positive. We also know that an is decreasing. Now, for something like this, I don't expect you to actually prove that it's decreasing, even though technically, yes, you could do like take the derivative and show that it's always negative. But this one, it's pretty obvious that it's decreasing. The numerator is constant and the denominator is just growing. So that's definitely getting smaller. One thing though, if you don't mention that it's decreasing, I'm going to assume you never thought about it, and that's a problem. So even if you don't prove something is decreasing because you think it's just painfully obvious that it's decreasing, you need to still state, hey, this guy is decreasing, because I need to know that you thought about whether or not it was decreasing. It's a very important thing to actually check. And the limit of an equals 0. Again, pretty obvious. You don't have to prove that, but you do have to state it so I know you thought about it. And so that means this series converges conditionally. So, without the absolute values, it actually converges by the alternating series test. So it converges conditionally by the alternating series test. So the first one converged absolutely. The second and third examples diverged, both with the test for divergence. The last example converged conditionally. We used a comparison to check the absolute convergence test. Didn't work out. We can't conclude from that the series diverges completely. What we do now is remove the absolute values, try a different test. In this case, the second go around, I tried the alternating series test, and I got that it converges. So ultimately, that ends that problem. Yeah. So hopefully that didn't go too badly. Hopefully you were all good boys and girls, and you actually paused the video when I asked you to pause it and actually tried it. So that's going to get you a lot more out of it. It's going to tell you, if you didn't get my answers, it's at least going to tell you where you're stuck, what are the kinds of things you might have to look into. If you didn't notice that you should have used something that I used, maybe you should look into that. Like if you didn't notice here, like if you did something besides the alternating series test, which I think is pretty much the obvious choice here, you're going to want to look into the alternating series test. Like, why would I choose that? And pretty much it's because I saw that minus 1 to the n right there. Yeah, that's it. How much time do we have? Okay. So we have about 17 minutes left. Don't know how much I can do in 17 minutes based on the next topic. But essentially, this ends series convergence tests. So when it comes to determining whether or not a series converges, and now we know how to determine whether it converges absolutely or conditionally or diverges using 10 tests that I've mentioned so far. And I also gave you the strategy for how to approach a series, a random series or several random series, and we actually went through a very long-winded example just now. Let's see. The next thing I want to talk about is estimating series. So, I mentioned this before. Figuring out what a series converges to is actually pretty difficult in general. Okay, so there were exceptions to this. We know for the geometric series, we actually know how to figure out what it converges to. For a telescoping series, we know how to figure out what it converges to, provided it is convergent. But all the other series tests, you'll notice they don't tell us what it adds up to. They just tell us whether or not it adds up to something out there. But let's say, for the sake of argument, because in the real world this is true, we need to know what it converges to. Or, as often happens in the real world, we need to know almost what it converges to within some tolerance. Usually, like I said, approximations is where it's at. In the real world, we run everything on approximations. Sometimes knowing the exact answer is not necessary. We just need to know that we're close enough to the exact answer for whatever practical purposes that we need. So one solution is to estimate a series using its partial sums, or one of its partial sums. So remember how I told you that finite series are useless? It turns out it's not exactly completely true. Basically, sometimes if we have an infinite series and we know it converges, but it's very important for whatever we're doing to know what it converges to, we do not have a good way of adding up an infinite number of values to get to the exact answer. What we instead do is add up a finite number of values, right? So given enough time and enough computing power, we are usually able to do that. So the thing is, though, how do we know how many terms to use, right? So, problem though, which partial sum? How do we know how many terms to use? And so this is the question I want to address now. I'm not going to address it in comprehensively because, one, it is above our pay grade. It's not really to deal with this. It's actually a more complicated topic than the series convergence topic all on its own. But there are a few instances in which we want students at this point to know how to actually estimate or approximate a series. And so the answer comes from series estimation theorems. So this is something that was studied, and we came up with several scenarios for how to judge how good an approximation is for a particular series. And in general, the estimation theorems fall in line with a particular convergence test that we're trying to apply. So if we know we're applying the alternating series test, there's a special theorem that will tell us how good a partial sums of an alternating series will work. Or if we use an integral test, there's a theorem that tells us how to find how close you're to the answer using an integral test. Or if you have a comparison test, there's a theorem that tells, right? So each of the tests I gave you before, they also have a theorem connected to them that talks about if you have to estimate the answer to this series that you just figured out converges using this test, here's a theorem that you can use to help you in that. I'm going to talk about several of them, but in the next 10 minutes, which it looks like that's what we have, I am going to talk about one of them. I think ultimately I'm going to mention maybe 3 of them. But I'll start with one that, traditionally speaking, this is always the one that they ask you about on like a departmental final. So, and that is the alternating series estimation theorem. So we'll cover approximately 3, the most important of which is the alternating series estimation theorem, because this is one where consistently I've seen them ask about approximating an alternating series. And I'm going to give you several examples of doing that later, because we're going to use that in future topics. But for now, I just want to talk about one of them. So this is estimation theorem. One, the alternating series estimation theorem. And I think I'll talk about one for the comparison theorem. I also think I'll talk about one for the integral test. And maybe I'll talk about a P-series one as well. I mean, I wrote down some of them that I wanted to talk about. I'm not going to talk about the one for the ratio or the root test, because those are actually pretty complicated to apply. But the alternating series test one is actually pretty simple to apply, which is why we like asking about it on finals. So whether you're doing a departmental final or you're taking my final, at some point, it's very, very, very likely that if we're asking about series at all, we're going to ask you to approximate one using this particular theorem. There are others, but in terms of what you need to know for a test, this one is definitely one you need to know. Here is what it says. Suppose this series converges to S, right? Where AN is always positive, right? So that's an alternating series, right? So it's an infinite series, and we have some reason to believe that it converges to S. Now, we don't necessarily know what S is. However, we do know how to judge how far away we are from S by taking partial sums. Then, it turns out that this distance, S, minus Sn, in absolute value. So if I want to find what is the difference between the nth partial sum, i.e. sum of the first n terms of the series, it turns out that if we add the first n terms of an alternating series, and I want to know how far away is that from the actual answer for the series, it turns out that that difference will be less than or equal to an plus 1 of all things. Very surprising. So that is called the alternating series estimation theorem. Pretty much, if you add up the first n terms of an alternating series and you want to know how close to the actual answer is these n terms that I just added up, then it turns out that the magnitude of the next term tells you how close you are. So let me give you an example here. Let me use an example that we've seen before. We know this series, the alternating harmonic series, converges. We use the alternating series test. Alright, so this was in the last class, or maybe the class before. We've done this problem. Okay, so we know this is an alternating series that converges. Here is a question. How good an approximation is S4 for the series? In other words, if I were to add up the first 4 terms, how close would I be to the actual answer if I were to add up an infinite number of terms? So we know that this guy, for example, is going to be -1 plus a half, minus a third, plus a fourth, minus dot, dot, dot. However, the first 4 terms, this is S4. Now, what is that going to actually look like? Let's actually do this. So S4 would be, the common denominator is 12. So -1 minus 12 over 12 plus 6 over 12 minus 4 over 12 plus 3 over 12. So that's -16 plus 9 minus 7 over 12. So S4 equals -7 over 12. And the question is, how close is this to the actual answer? That's the question. Well, it turns out that the difference between S and -7 over 12 is going to be less than or equal to A5. Specifically the 5th term. Now what's the 5th term? The 5th term that we would have written down here would be 1 over 5. Right? This is actually A5. Right? So this is A1, A2, A3, A4, A5. Now A5 is 1/5. In other words, that's 0.2. In other words, -7 over 12 is within 0.2 of the actual sum. So I have this series. It's an infinite alternating series. And of course, I don't have the time or resources or sophistication to add up an infinite number of these terms. What I could do, let's say I added up the first 4 terms. How good is that? How good an approximation is that to the actual answer? Turns out that the 5th term is going to tell me how good the first 4 terms is as an approximation. So if I add up the first 4 terms, the 5th term is going to tell me how close I am to the answer. If I add up the first 100 terms, the 101st term is going to tell me how close I am to the actual answer. So if I'm in a situation where I don't care if I'm off by 0.2, then adding up just 5 terms of this series is actually going to be a good idea. It's actually going to be pretty useful to actually add up the first 5 terms, first 4 terms. So that's the alternating series approximation theorem. You pretty much apply like that. So if you add up n terms, the very next term, its magnitude, is going to tell me how close we are to the actual answer. So it's pretty nice, pretty aesthetic or elegant for an alternating series. And so it's something that we'll ask you about a lot. Here's a question, food for thought. Hopefully you got that. If not, you can ask me about it. We'll talk about it a little bit more next time. But let's say I know ahead of time what tolerance I would like. So I'll leave you with this question and that ends the lecture. Question. How many terms are needed to approximate? Let's look at the same series. Within 0.01 accuracy. So let's say I only want to be off by 1/100th of the actual answer or less. How many terms of the series would I need to add? So think about that for next time, and we're going to wrap that up. Hopefully that was clear, hopefully that was helpful, hopefully you did what I asked and paused the video and tried problems when I asked you to. But we'll pick up with that from here next time. And we'll start with thinking about this question right here. That's it. I will see you guys. Stay safe. Wash your hands, 20 seconds at least. And I'll see you in the next one. Ciao.